So my topic is network covalent solids, molecular solids, and polymers. And so to kind of relate it back to the big idea of this, so there's network covalent solids, which is actually a subsection of atomic solids. So molecular solids is actually going to be a different category. And they're going to be solids made of atoms or molecules held together by intermolecular forces. And an important thing to note is that they have strong intramolecular forces but weak IMFs that lead to a low melting point, and they're actually going to be insulators and soft and gases or liquids at room temperature. And some examples would be NH3, N2, argon solid, and dry ice. Network covalent solids. So this is a picture depicting a couple of things. So you can see the structure of a lattice structure of ions, but you can also see graphite and diamond, which are two different types of network covalent solids, and of course ice. So network covalent solids are solids that consist of atoms held together in large networks or chains with and these covalent bonds are actually going to be going to lead to large molecules because of the strong directional quality to them, and they're going to be high melting points and hard, and we can't actually say the property because it's actually going to depend on the substances, so I'm going to go into further detail. So this is a diagram that you can pause right now and take a note, but I'm actually going to go into further detail. So network covalent solids, so allotropes are single element compounds with different structures. So the major allotropes are going to be diamond, graphite, fullerene. Okay, so diamond is shown on the right, and it's actually going to be a carbon atom that's going to be tetrahedral and have a coordination number of 4 for each one, and it's going to be strong due to the overlap of the sp3 orbitals, and this is going to mean that there's going to be no free orbitals left over, which means it's going to be non-conductive and act as an insulator, but it's also going to have a high melting point, and it's going to be hard and colorless. But graphite, on the other hand, is actually going to be soft, and the layers of carbon rings, as you can see, are going to be on top of each other, but they're going to be held by weak forces, but the strong covalent bonds between each carbon atom is going to be arranged in a planar hexagonal ring, and that's going to leave a unhybrid p orbital. And so with the delocalization of electrons, it's actually going to make it a conductor, and there's going to be a high melting point, and it's going to be actually a good lubricant. But it's important to know that it's going to be slippery, and it's actually going to be soft because of the adjacent layers that can actually slide past each other easily. And the 2D network or structure is going to reflect the covalent bonds. So fullerenes are going to be buckyballs and nanotubes, and buckyballs are spherical, and you know that by balls, and nanotubes, it's going to be tube-shaped, an example graphene. And so the properties of this are going to be super strong, super light, flexible, and it's important to relate to the free radical scavenger when discussing this, because it's going to make it an electron sink because it's going to be really conductive. And silicon actually is very special because it is going to have a different molecular orbital arrangement than the diamond, and this is going to allow it to actually be a semiconductor. So doping is going to be when you add impurities to semiconductors to improve its conductivity. And so n-type doping is when you're adding it to the next group and causing an extra negative charge, and the negative charge is going to come from the extra valence electron, but p-type doping is from the previous group and is going to cause a positive charge. And what this does is there's actually going to be a hole from the p-type doping, and this allows the electrons kind of jump around. And bond theory is also important to discuss when you're talking about doping, because that's kind of the reasoning behind it all. And polymers, the final thing. So with polymers, it's actually a large molecule composed of monomers, and most macromolecules are actually polymers. So that's why the main discussion with this is biochemistry and macromolecules. And so the three main polymers of macromolecules are going to be carbohydrates, proteins, and nucleic acids. So proteins is going to be amino acids are the monomers, and so them combined are make polymers, and peptides, of course. And so the IMFs in proteins are what dictate the shape and the different structures. So with secondary structures, there's beta-plated sheet and alpha helix, and they're going to be determined by the hydrogen bonds between the functional groups. But tertiary, as you can see in the picture on the right, it's going to be R groups with ionic and disulfide bridges that determine the IMFs. But quaternary structure is what's going to happen with the multiple polypeptides, and that's going to result in a bunch of hydrophobic attractions and hydrogen bonding. And DNA is going to basically be what we've learned about hydrogen bonds, and there's going to be a covalently bonded between each individually. Okay, So the order would be the molecular solid, then the network covalent solid, and then the ionic. And then the SiO2 is the actual atomic solid, and specifically the network covalent solid. And then when discussing the future, it would be the wide bandgap semiconductors that we talked about from 2 months ago in the video of Department of Energy. And the silicon has the carbon different arrangement. That's why it can be a semiconductor versus a diamond. And then when we're specifically talking about semiconductors, you'd talk about the N-type doping, P-type doping, and bond theory.